Now we're going to be working on our last form of induction, and it's called strong induction. So we're going to review ordinary proof by induction. Then we're going to extend the reasoning that we used in proof by induction to be able to strengthen the induction hypothesis. In other words, we'll be able to assume more during the inductive step. Then we're going to see how strong induction reasoning works on the fundamental theorem of arithmetic, and then we're going to prove the fundamental theorem of arithmetic using strong induction. All right, so here are the steps that we use to prove a theorem using induction. First thing we do is the basis step, also known as the base case. We prove the theorem for the very first case in the theorem. Usually that's n equals 1, but as we saw in the last video, it could start literally anywhere. Our inductive step is then when we assume the theorem is true for n equals k, and then prove the theorem is true for n equals k plus 1. Now I want to take a step back and sort of think about why we're allowed to assume the case n equals k when we are proving the case n equals k plus 1. Well, we got to remember the reasoning we used behind induction in the first place. Our reasoning was that we imagining proving all the cases in order, starting with the first value of n, our base case. And that's our basis step, right? So then our inductive step is how we get from each step that we just did to the next step, n equals k plus 1. So we can think of the n equals k step as the case we just proved, and that means we can assume it. Similarly, we can think of the n equals k plus 1 case as the next case that we're going to prove, so we use the n equals k case to prove it. So we assume the n equals k case because, in principle, that is the step that we just proved. And this demonstrates how every case is proven, how we use each case that we just proved to prove the next one. But if you look really closely at this process, we're not using the full strength of what we know. For instance, let's think about when we're trying to prove the n equals 4 case. Well, we just proved the n equals 3 case, so we know that one is true. Right? We just proved it. But right before the n equals 3 case, we also verified the n equals 2 case. And right before the n equals 2 case, we did the n equals 1 case. So actually, it's not just the n equals 3 case that we've done, but the n equals 1, 2, 3, all three of those cases. Which means that if there's nothing logically incorrect about assuming that n equals 1, n equals 2, and n equals 3 cases are true. We can assume those as part of our induction hypothesis in order to prove the n equals 4 case. So we don't just have to rely on the n equals 3 case to prove the n equals 4 case. We can rely on any case that came before n equals 4 in order to do that. In general, if we want to prove the n equals k plus 1 case, which is what we do in induction, we should be allowed to assume all the cases n equals 1, 2, all the way through k. So here are the steps that we can use in proving a theorem by strong induction. First is our basis step, base case. It's the same as all the other inductions. Prove the theorem for the first case. Again, use the n equals 1, but is really the first n that is mentioned in the theorem. Our inductive step, we assume that the theorem is true for all cases n, not just n equals k, but n less than or equal to k as well. And then we prove the theorem is true for n equals k plus 1. And again, I didn't mention what the lowest value of n could be in that inductive step, but it is the base case, because the base case is the first one that you prove, so you can only assume all the way down to the base case. So from the base case up to n equals k. All right, so let's demonstrate this reasoning that we use for strong induction on the fundamental of arithmetic, and then we'll do a proof by a strong induction. So suppose n is a natural number with n greater than or equal to 2. Then we're going to prove that either n is a prime number or it is a product of prime numbers. So we're proving that every number that is at least 2 has a prime factorization, which we kind of know to be true from our experience, but now we're going to prove it. So let's look what strong induction looks like in some cases, right? So I'm going to use strong induction reasoning so we get an idea of what the proof is going to look like. So for n equals 2, well, that's our base case, right? N equals 2, 2 is prime, so we're done. N equals 3, that one's also prime. Can't say much more than that it's prime. n equals 4 is the first interesting one, right? Because that is the first one that is not prime. So how do we use in our previous cases to do n equals 4? Well, the fact that n equals 4 is not prime means that we can factor it into two other numbers. So in this case, 2 times 2. And we know from the n equals 2 case that 2 is prime, right? The n equals 2 case says that 2 is prime. We're looking back at our previous cases. And so since 2 is prime, that means n is a product of primes, 2 times 2. One thing I want you to notice about what we did here is when we proved the n equals 4 case, we didn't use the n equals 3 case. In fact, the n equals 3 case was completely useless to us for n equals 4. We needed to step all the way back to the n equals 2 case in order to help us prove that particular case. All right, so for n equals 5, that one's boring. 5 is a prime. N equals 6, this one's kind of interesting. We got n equals 2 times 3. Now in this one, we have two different numbers that are smaller, right? So we've used the fact that n is equal to 2 times 3. We know that 2 and 3, by our previous cases, they're either prime or products of prime. I mean, we know they're prime, but based upon our assumptions from what we've done before, if we've sort of forgotten what we've done, we know that we either prove that 2 is prime or it's a product of primes, and we either prove that 3 is prime or a product of primes. In either case, we can shove those primes together to make n a product of primes, and then that's our theorem. And then n equals 7, that's a prime. N equals 8, again, we want to break it down into smaller numbers so we can use our induction hypothesis. N equals 2 times 4. We know that 2 and 4 are both either prime or products of primes. So we're going to smash those primes together to make n a product of primes. So you can see, first of all, how we're using strong induction reasoning to prove this theorem. But then also, maybe you can see what our strategy is going to be when we're actually proving this theorem. All right, so here's our strategy. So we're assuming that all the numbers between 2 and k have a prime factorization. They're either prime or a product of primes. Now we want to prove that n equals k plus 1 is either a prime or a product of primes. So what's our general strategy? Well, we first want to check to see if our number n is prime or not. Right? If it is prime, then we're done, right? We know it's prime. That means it's either prime or a product of prime numbers. We're done. If it is not prime, our strategy was to, well, we wanted to break it down into smaller numbers. So we factored it into two smaller numbers that multiply to the number. Then we apply our induction hypothesis to each of those individual factors. And then we smash those, right, that they are prime or a product of primes. Then we smash all those prime numbers together to give you the prime factorization of the number n. And that'll prove our final result. All right, so here's what our proof is going to look like. So first of all, remember to be nice to our readers. We're going to tell them what proof method we're using. We're going to tell them we're going to prove the result by strong induction. Right? And that tells them not only are we going to use induction, but we're not going to use the step we just did. We're going to reach back a little bit further. And if you want, you can call it what Uncle Ted calls it, the second principle of induction. That's fine too. So first we're going to do the base case, that is n equals 2. We know that 2 is a prime number, so our basis step is proven. For the inductive step, we got to tell the reader what we're going to assume, what we're going to show. We're going to assume the theorem is true for all n between 2 and k, where k is at least 2. And then what that means is we're going to assume that every natural number n between 2 and k is either prime or can be written as a product of prime numbers. Then we're going to show that n equals k plus 1 is either prime or can be written as a product of prime numbers. Now remember, what we were doing in the previous slides is we took two cases. One, we looked at our number n is prime, and one when it's not prime. So that indicates that we're going to do a proof by cases. So what we're going to say first is it is clear that k plus 1 is either prime or not prime. That means we're going to consider each of these cases separately. So we're both justifying that we're telling our reader what the cases are and justifying why those are the only cases that we have to consider. So in the case that k plus 1 prime, we are done because k plus 1 is prime. In the case that k plus 1 is not prime, that means we can factor it into smaller numbers. So k plus 1 is equal to r times s, where r and s are natural numbers. And we know that r and s are between 2 and k because they're both smaller than k plus 1. By the induction hypothesis, right, the induction hypothesis says that r and s are either prime or products of prime. We can write r and s as the product of primes, or if where pi is a prime and qi is a prime number, Or if we want to think of r being a prime number, we can just say, well, in that case, we just let j equals 1. If j equals 1, that means there's one prime in the factorization. That means r is prime. And similarly, we can let k equal 1 if s is a prime number. We then have, well, k plus 1 is equal to r times s. We can substitute in the prime factorizations for r and s. And then that is a product of prime numbers. The p's are prime, the q's are prime, so that is writing k plus 1 as a product of prime numbers. That completes the proof. All right, so I think you're ready to work on the remaining activities that you couldn't get to because they needed strong induction. Those are on the PDF file included with this video.